Let us continue with our running example of GCD to explore more issues involved with programming. We started with the basic definition of GCD, which said that we should first compute all the factors of m, store it in a list, compute all the factors of n, store it in another list. From these two lists, extract the list of common factors and report the largest one in this common factor list. Our first simplification was to observe that we can actually do a single pass from 1 to the minimum of m and n and directly compute the list of common factors without first separately computing the factors of m and the factors of n. We then observed that we don't even need this list of common factors since our interest is only in the greatest common factor or the greatest common divisor. So we may as well just keep track of the largest common factor we have seen so far in a single name and report it at the end. Our final simplification was to observe that if we are interested in the largest common factor, we should start at the end and not the beginning. So instead of starting from 1 and working upwards to the minimum of m and n, it's better to start with minimum of m and n and work backwards to 1. And as soon as we find a common factor, we report it and exit. Remember always that 1 is guaranteed to be a common factor. So when we start from minimum of m and n and go backwards, if we don't see any other common factor, we are still guaranteed that we will exit correctly when we hit 1. So what we noticed was that though these different versions are simpler than the earlier versions, they all have the same efficiency in terms of computation, which is that they will force us in the worst case to run through all the numbers between 1 and the minimum of m and n before we find the greatest common factor, whether we work forwards or backwards. So at the time of the ancient Greeks, what was possibly the first algorithm in modern terminology was discovered by Euclid, and that was for this problem, GCD. So what Euclid said was the following. Suppose we have a divisor D, which divides both m and n. So this is a common divisor, and we are looking for the largest such D. Let us assume also, for the sake of argument, that m is greater than n. So if D divides both m and n, we can write m as a times d and n as b times d for some values a and b. So m is a multiple of d and so is n. So if we subtract the left hand side, the equations, then the left hand side is m minus n. So we take m and subtract it n from m. So correspondingly we subtract bd from ad. So m minus n is equal to ad minus bd. But since d is a common term, this means m minus n is a minus b times d. So this is where we are using the assumption that m is greater than n. So a minus b will be a positive number. But the important thing to note is that m minus n is also a multiple of d. So in other words, if d divides both m and n, it also divides m minus n. And since d is the largest divisor of m and n, it will turn out that d is also the largest divisor, which is common to m, n and m minus n. In other words, the GCD of m and n is the same as the GCD of the smaller of the two, namely n, and the difference of the two, m and n, m minus n. So we can use this to drastically simplify the process of finding the GCD. So here is the first version of Euclid's algorithm. So consider the value GCD of mn, assuming that m is greater than n. So if n is already a divisor of m, then we are done and we return n. Otherwise, we transform the problem into a new one, and instead of computing the GCD of m and n that we started with, we compute the GCD of n and m minus n and return that value instead. So here is a Python implementation of this idea. So there are a couple of new features that are introduced here. So let us look at them. The first is this special statement which starts with the symbol hash. So in Python, this kind of a statement is called a comment. So a comment is a statement that you put into a program to explain what is going on to a person reading the program, but it is ignored by the computer executing the program. So this statement says that we are assuming that m is bigger than or equal to n. So this tells us that when the program continues, this is the assumption. Of course, it is possible that the person who invokes GCD does not realize this. So they might invoke it with m smaller than n, and so we fix it. So this is a special kind of assignment which is peculiar to Python. It is not present in most other programming languages. So what we want to do is basically we want to take the values m and n and we want to exchange them, right? So we want to make the new value of m the old value of n and the new value of n the old value of m, so that in case m and n were in the wrong order, we reverse them. So what this Python statement does is it takes a pair of values and it does a simultaneous assignment. So it says that the value of n goes into the value of m and the value of m goes into the value of n. Now it is important that it is simultaneous, because if you do it in either order, if you first copy the value of n into m, then the old value of m is lost. So you cannot copy the old value of m into the new value of n because you have lost it. Right? So imagine that you have 2 mugs of water, right? And now you want to exchange their contents. Now you have to make space. You cannot pour this into that without getting rid of that. And once you got rid of that, you can't pour that into that. So you need a third mug normally. So you need to first transfer this here and keep it safe. Then you need to transfer this there, and then you need to copy it back. So this is the normal way that most programming languages would ask you to exchange 2 values. But Python has this nifty feature by which you can take a pair of values and simultaneously update them. And in particular, this simultaneous update allows us to exchange the values without worrying about having this extra temporary place to park one value. So anyway, all that this first part is doing is to ensure that this condition that we have assumed is satisfied. So now we come to the crux of the algorithm. So if n divides m, that is the remainder of m divided by n is 0, then we have found n to be the GCD and we return n. If this is not the case, then we go back to what we discovered in the last slide, and we now are going to compute the GCD of n and the difference m minus n. So we would ideally like to compute GCD of n and m minus n. So we compute the difference is m minus n, and we could just invoke this. But it is possible, for example, if m is say 97 and n is 2, then the difference will be 95. So the difference could very well be larger than n, and we would ideally like to call this function with the first number bigger than the larger number. So we will just ensure this, even though our function does take care of this. What we want to do is we want to call GCD with n and m minus n. Instead, we will call GCD with the maximum value of n in the difference as the first argument and the minimum value of n in the difference. So it will make sure that the bigger of the 2 values goes first and the smaller of the 2 values goes. And whatever this GCD, the new GCD returns, is what this function will return. Right? So this is an example of what we will see later, which is quite natural, which is called recursion. Recursion means that we are going to solve this problem by solving a smaller problem and using that answer, in this case directly, to report the answer for our current problem. So we want to solve the GCD of m and n, but the GCD of m and n, instead we solve the GCD of n and m minus n, and whatever answer that gives us, we directly report it back as the GCD for this number. So we just invoke the function with the smaller values and then we return it. Now whenever you do a recursive call like this, it's like a while loop. It will invoke the function again, that in turn will invoke a smaller function and so on. And you have to make sure that this sequence in which GCD keeps calling GCD with different values doesn't get into an infinite progression without a stopping point. So formally, what we have to ensure is that this guarantee of finding an n which divides n. So this is where GCD actually exits without calling itself. So we have to make sure that eventually we will reach this point. Now what is happening, if you see here, is that the values that are passed to GCD are getting smaller and smaller. Now what can we have for m minus n? What can be the value? Can it be 0? Well, if m minus n is 0, that means m is equal to n. If m is equal to n, then certainly m is divisible by n. So if m minus n is 0, then it would have exited, so it cannot be 0. So it must be at least 1. So whenever we call this function, m minus n is at least 1. On the other hand, each time we are reaching smaller values. So we start with some value and m minus n keeps decreasing. What happens when it actually reaches 1? Well, when it reaches 1, then 1 divides every other number. So m percent n or m divided by n, the remainder will be 1, will be 0, right? So we will return GCD of 0. In other words, we are guaranteed that this function, because it keeps reducing the number that we invoke the function with, will eventually produce a call where this number, where GCD terminates. So this is important, and we will come back to this later, but whenever you write a function like this, you must make sure that there is a base case which will be reached in a finite number of steps, no matter where you start with. Right? So this is Euclid's algorithm, the first version, where we observe that the GCD of m and n can be replaced by the GCD of n and m minus n. And what we have seen in this particular implementation are three things rather. We have seen how to put a comment in our code. We have seen that Python allows this kind of simultaneous updation of two variables at the same time, so m comma n equal to m comma n. And we have also seen that we can use the same function with new arguments in order to compute the current function. Right? So there is no problem with saying that in order to compute GCD of m and n, I will instead compute GCD of some other value and use that answer to return my answer. So let us look at a different version of this algorithm where we replace the recursive call by a while loop. So we saw while in our last version of the standard algorithm when we were counting down from the minimum of m comma n to 1. So we kept checking whether I was greater than 0 and we kept decrementing. Well, here we are doing the recursion using a while. So the first thing to notice here is that I have moved this comment which used to be in a separate line to the end of a line. So what Python says is that if there is a hash, then the rest of the line can be ignored. So it reads this line, it sees a valid conditional, and then it sees a hash. So it's as though this statement was not part of the Python program when it is executing. So a comment can either be in a separate line or it can be an end of a line. Of course, remember that you cannot put anything after this which you want Python to execute, because once it sees a hash, the rest of the line is going to be ignored. So it can't be in the middle of a line. You can't put a comment in the middle of a line, but you can put it on a separate line or you can put it at the end of a line. So anyway, so this is our comment as before. So up to here, there's no change except that I've shifted the comment position. So now we reach this point where we actually have to do some computation. So at this point, if we have found n such that n divides m, we are done and we can directly return n. So this is what our recursive code would do. If we have not found such an n, we have to do some work. So the condition is to check whether m divided by n actually produces a remainder. So this not equal to symbol is written with this exclamation mark. So this is the same as the mathematical not equal to. Remember that this double equal to was what we use for the mathematical symbol of equality. So this is our symbol for not equal to. So long as there is a remainder, that is the remainder m divided by n is not 0, we do what we did before. We compute the difference and we replace m by the maximum of the two values and n by the smaller of the two values. So we have a pair mn whose GCD we are trying to find, right, with the assumption that m is bigger than n. At each step, we replace m by the larger of n and the difference and n by the smaller of n and the difference. So this is exactly what we are doing in this recursive call. We are saying, pretend we are computing the GCD of that. So here in this while loop, effectively we are saying replace the computation of mn by the the GCD of mn by the computation of maximum n diff and minimum n diff. And we keep doing this until we hit a condition where n actually divides n. And exactly like we said in the recursive case, that there will be a boundary case where at the worst case n will become 1 and 1 will divide everything. In the same way here, the difference will keep reducing. The difference cannot be 0 because if the difference is 0, it would have divided. So the difference can at most go down to 1, and when it hits 1, we are done. So this is a while version of the same recursive function we wrote earlier. So if it helps, you can look at these side by side and try to understand what the recursive thing is doing and what the while is doing, and see that they are basically doing the same thing. And the idea that the recursion must terminate is exactly analogous to the claim that we said earlier, that when you write a while, you must make sure that you make progress towards making the while condition false so that the while exits. So just like the recursion can go on forever if you're not careful and you don't invoke it with arguments which guarantee termination, the while can also go on forever if you don't make progress within the while in order to make sure that the while condition eventually becomes false. So we can actually do a little better than this. So let us see one problem with this by doing a hand execution. So supposing we start with some number like GCD of 101 and 2. Then our algorithm will say that this should now become GCD of the difference and n. The difference is 99, so we'll have 99 and 2. And then this will become GCD of 97 and 2, and so on. So we'll keep doing this about 50 steps, and then eventually we will come down to GCD of 5 and 2, and then GCD of 3 and 2. And now when we compute the difference, we'll get GCD of 2 and 1. So now the difference will become smaller. And then at this point, we will report that the answer is 1. So it actually takes us about 50 steps in order to do GCD of 101 and 2. So one of our criticisms of the naive approach is that it takes time proportional to the numbers themselves. If we had numbers m and n, we would take in general a number of steps equal to minimum of m and n. Now here in fact we are taking steps even larger than the minimum, because the minimum is 2. Right? If we were just computing factors, we'll say that there's only factor of 2 is 2 and it's not a factor of 101, and we would have stopped right at the beginning. So this actually seems to be doing worse than our earlier algorithm in certain cases. So here is a better observation. So suppose n does not divide m. In other words, if I divide m by n, I will get a quotient and a remainder. Right? So I can write m as q times n plus r, where q is the quotient and r is the remainder. So you may remember these terms from high school arithmetic. So this is n goes into m q times and leaves a remainder r, and we are guaranteed that r is smaller than n. Otherwise, it could go one more time. It will become q plus 1. Right? So we have a remainder r which is smaller than n. So for example, if I say 7 and I want to divide it by 3, for example, this will be 2 times 3 plus 1. So this will be my quotient and this will be my remainder. And the important thing is the remainder is always smaller than what I'm dividing by. So now let's assume as before that we have a common divisor for both m and n. Okay? In other words, like before, we can write m itself as a times d and n as b times d for some numbers a and b, because m is a multiple of d and so is n. So if we plug this into the equation above here, right, then we see that m, which is a times d, is equal to q times n, which is b times d, plus r. So d divides the left and d divides one part of the right. Okay? So you can easily convince yourself that d must also divide r. Okay? So the way to think about it, if you want pictorially, is that I have this number m, and I can break it up into units of n, and then there is a small bit here. On the other hand, if I look at d evenly divides everything. Okay, so it divides each of these blocks. It also divides the whole thing. But okay, now if I continue with d, it is going to stop exactly at this boundary, because d also divides n. Therefore, d must also divide this last bit, which is r, exactly. So in other words, we can argue very easily that r must also be a multiple of d. So d must divide r as well. Right? So if d divides m and d divides n, then d must divide the remainder of m divided by n. And as we saw before with the difference, so last time we said we would look at the difference m divided by n. Now we are saying we look at the remainder of m divided by n, and d must divide that, and d will be in fact the GCD of n and this remainder. So this is an improved, and this is the actual version of the algorithm that Euclid proposed, not the difference one, but the remainder one. It says, consider the GCD of m and n assuming that m is bigger than n. Now if n divides m, we are done. We just return n. This is the same as before. Otherwise, let r be the remainder, okay, is the value of m divided by n, get the remainder, and return the GCD of n and r. And at this point, one important thing to remember is that r is definitely less than n. So we don't have to worry about this condition here. We don't have to take the max and the min as we did for the difference, because the remainder is guaranteed to be less than n, otherwise n would go one more time. So as before, we have a very simple recursive implementation of this, and this is even simpler because we don't have to do this max min business. So like the previous time, we first flip m and n in case they are not in the right order. Okay. Then if n divides m, if m, the remainder of m divided by n is 0, we return n and we are done. Otherwise, we return the GCD of n and the remainder. So this is the remainder. And remember that the remainder is always less than n, so we don't have to worry about flipping it and taking max and min at this point. And analogous to the previous case, we can do this whole thing using a while instead of doing it with the recursive thing. So we first exchange m and n if they're in the wrong order. Then so long as the remainder is not 0, we replace m by the smaller of the two numbers, and we replace n by the remainder, and we proceed. Now we are guaranteed that this remainder will either go to 0, but if it goes to 0, it means it divides. Or if it's not 0, in the worst case, the remainder keeps decreasing because it's always smaller than the number that we started with. So it keeps decreasing, and if it reaches 1, then in the next step it will divide. So finally we will return at least 1. So if we go back to the example that we were looking at, so if we saw that GCD 101, 2, when we did it using the difference, we said we took about 50 steps. Now here, if we do the remainder, I'm going to directly find that the r is equal to 1, right? If I divide 101 by 2, it goes 50 times, the remainder 1. So in one step, I'll go to GCD of 2, 1, and I'll get 1. So in fact, what you can show is that this version with the remainder actually takes time proportional to the number of digits. So if I have, say, a 100-digit number, okay, it will take about 100 steps. So for instance, if we have a billion as our number, so a billion will have about 10 to the 9, will have about 10 digits. Okay. Then if I do the naive algorithm, then it could take some constant times a billion number of steps, so say a billion steps. But this algorithm, because of the claim that it takes time proportional to the number of digits, since the 10 to the 9 has approximately 10 digits, it will only take about 10 steps. So there's a dramatic improvement in efficiency in this version. So this is something that we will touch upon while we are doing this course. So this course is about programming, data structures, and algorithms. So the programming part talks about what is the best way to express a given idea in a program in a way that it is easy to make sure that it is correct and easy to read and maintain. So that is the programming part. So how do you write, how do you express your ideas in the most clear fashion? But the idea itself has to be clear, and that is where data structures and algorithms come in. Right? So you might write beautiful prose, but you may have no ideas, or you may have very brilliant ideas, but you may express yourself clumsily. Neither of them is optimal. So this is like writing in any other language. Right? So you may have brilliant ideas to express, but if you cannot convey them to the person you're talking to, the ideas lose their impact. So you need ideas and you need a language to express them. So programming is about expressing these ideas, but the ideas themselves come from algorithms and data structures.